All right, our next video in our solution unit deals with a term that's called dilution. And when we talk about dilution, or if we're diluting something, normally when you think of dilution, you're thinking of taking a concentrated solution and making it not as concentrated. And that's exactly what diluting a solution is you're taking a concentrated solution and you're making it not as concentrated. So, for example, here we can see an example of this where this here would be the concentrated solution. And so what they've done is they've taken a small amount of it here and they've placed it into a flask, and then they have added some water to it. And then they did it again. They took a small amount and added some more water to it. And you can see each time the color of the solutions gets less and less dark because we're adding more and more water and less of the original solution. So dilution is the process of preparing a less concentrated solution from a more concentrated one. So we're starting with a solution with a high concentration and we're going to a solution that has a concentration not as high. And as we've learned up until now, we know that when we talk about concentration, we are referring to the molarity of the solution, the moles of the solute divided by the liters of the solution. Okay, now one thing that's important here is the moles of the solute before the dilution equals the moles of the solute after the dilution. We'll talk about what that means here in just a little bit. So, for example, what we see here is we have a certain number of molecules of whatever in the solution. And what we're going to do is we're going to add some more solvent. And remember that in most cases, the solvent is going to be water. So if we add more water to the solution, have we changed the moles of our solution? And clearly, the answer is no. The same number of moles or molecules is there as was there before. So here when we said the moles of the solute before equals the moles of the solute after, that is accurate. The number of molecules that are dissolved in the water or whatever the solvent is still the same before the dilution and after the dilution. Now, of course, that's a qualitative way of thinking about it. We also need to look at it quantitatively involving numbers. And so the general formula that we use when we do dilutions looks like this. M1V1 equals M2V2, where the M1 and the V1 refer to the initial concentration or the initial molarity here times the initial volume. And that is equal to the final concentration times the final volume. Obviously, the molarity is in moles over liters. The volume must be in liters. And that will make your math just much simpler when solving these types of problems. So here's an example. How would you prepare 60 milliliters of a 0.2 molar HNO3 from a stock solution? Now the word stock kind of just means that that's the one you're pulling off the shelf. That's the one you have in stock. It's just a word that you see in chemistry quite a bit. So this basically means your initial solution is a 4 molar nitric acid solution. So what we're trying to do is we're trying to create 60 milliliters of a 0.2 molar nitric acid solution. So let's think about our equation. M1V1 equals M2V2. So our initial concentration, this one right here, is our 4 molar HNO3. So we're going to go 4.00 molar. Our V1 is actually what they're asking you about. They're asking you how much of that 4 molar HNO3 would you need. So I'm going to leave that as V1. My final concentration needs to be 0.2 molar. And how much of that do I need? I need 0.060 liters. Notice my volume, I did convert from milliliters to liters. So now to solve this problem, I need to get V1 by itself. And in order to do that, I'm just going to divide both sides by the 4 molar. So that whole thing cancels. So V1 is equal to, now I'm going to pull out my calculator, 0.2 times 0.060 divided by 4. And that equals, so V1 is equal to 0.003 liters. Because we use milliliters up here, I'm going to convert that back to milliliters. So I'm going to move the decimal point 3 spaces to the right, which is 3 milliliters. So that means that in order to create this solution, I would need 3 milliliters of this concentrated, of this stock 4 molar nitric acid. Now, that doesn't quite answer the question. The question is, how would you prepare this? Well, we know that we would take 3 milliliters of our 4 molar nitric acid, but then what would we do? Are we done? Are we simply taking 3 milliliters of this concentrated acid? Of course not. We come back here. What did we do to make these solutions here less concentrated? How did we dilute them? We added water. And so what we don't see in this equation that we just learned is how much water do we need to add. And we don't specifically write an equation for it because we know that if we need 60 milliliters of this and we've got 3 milliliters of the strong acid, how much water are we going to need? Oh, we're going to need 57 milliliters of water. And so all total, we end up with 60 milliliters of a solution that includes 3 milliliters of the concentrated stuff, 57 milliliters of the water, and that creates a 0.2 molar solution of nitric acid. Okay, let's look at another dilution problem. It says if 32 milliliters stock solution of 6.5 molar H2SO4. Now, let me just give you an idea. What we typically use in our classroom is 1 molar, maybe 2 molar. Once you start getting up in the higher numbers, the 6.5 molar, a lot of times you can have 12 molar. You can have some really, really concentrated stuff. When you get up into the 12 molar range, you're talking about acids that are really, really strong, and you're talking about, if it gets on your skin, really, really dangerous. So a lot of times what we do is when we buy this stuff, we buy it really, really concentrated, and then what do? So we can use it in the classroom? We dilute it. And so we don't have to pay for a whole bunch of water that we're buying. We're buying mostly acid, and then we just dilute it using this exact formula that we're learning today. So 6.5 molar is getting up there. That's a pretty strong acid. That's one where I would definitely be wearing gloves. I might even be wearing something protecting my breathing simply because, you know, a lot of those vapors can be potentially dangerous as well. So 32 milliliters of a stock solution of 6.5 molar H2SO4 is diluted to a volume of 500 milliliters. What is the concentration of this resulting solution? So let's think about our equation again. M1V1 equals M2V2. Now when we'll put these numbers in, our initial concentration goes here. That's our 6.5 molar. We've got 32 milliliters of it. 0.032 liters is going to equal our final concentration. That's what they're asking us about. What's the resulting concentration? And then our final volume is going to be 0.5. Now, I know what you're thinking. You're probably thinking, oh, wait a minute. If our milliliters are going to cancel anyway, can't we just leave it in milliliters? And the answer to the question is yes, you actually could. We're not like you were using the gas constant or anything like that. You'll notice that to get M2 by itself, you're just going to divide by 0.5. And the milliliters are going to cancel just like the liters would. Or excuse me, that's liters, not milliliters. The liters cancel just like the milliliters would. So technically you can. I just find it easier, just like with gases. Just put it into liters and then there's no problem. So I'm going to take 6.5 times 0.032 divided by 0.5 equals a final concentration of 0.416 molar. So by adding what? 468 milliliters of water to the solution, we're taking the concentration from a 6.5 molar solution all the way down to a much safer, a much classroom-friendly concentration of 0.416 molar. Okay, here's another example. It says in an experiment, a student needs 250 milliliters of a 0.1 molar copper 2 chloride solution. A stock solution of 2 molar copper 2 chloride is available. How much of the stock solution is needed? So this is kind of like the first problem that we did, where we had to figure out how much of that original concentration we needed to create our final concentration. So again, M1V1 equals M2V2. Our initial concentration is 2 molar. Our initial volume is what we're looking for. How much of this stock solution do we need? Our final concentration, we want to be 0.100 molar, and we want 0.250 liters of it. So now to get V1 by itself, again, we're going to divide by 2. So 0.1 times 0.250 divided by 2. My initial volume is 0.0125 liters, which is equal to, move the decimal point 3 spaces over, 12.5 milliliters. So again, let's look at the question. How much of the stock solution is needed? 12.5 milliliters. The second part says, describe the steps needed to create the actual solution. So again, we would take 12.5 milliliters of our 2 molar copper 2 chloride. So step 1 would be, using a graduated cylinder, obtain 12.5 milliliters of the 2 molar copper 2 chloride. And then you would add water until you reach 250 milliliters. Now, in this case, it's not really a guessing game. If you have 12.5 milliliters of the copper 2 chloride solution, which again is still mostly water, now you're going to simply add water. You're going to add, let's take 250 minus 12.5 is 237.5 milliliters. So 237.5 milliliters of water and 12.5 milliliters of the 2 molar copper 2 chloride is going to create a 0.1 molar solution of copper 2 chloride. All right, our last one here. Let's see here, make sure we're doing this okay. Our last one, if it'll let me close this. I guess we're still, let's see here. Okay, here we go, sorry. Okay, so our last one here. Not sure what this is doing here. What volume of 12 molar hydrochloric acid? So that is basically when we buy hydrochloric acid from like Flynn Scientific, that's one of the big chemical companies. This is how they sell it to us, is they sell it to us in terms of in really, really concentrated stuff. So what volume of 12 molar hydrochloric acid, the stock solution, must be used to prepare 150 milliliters of 0.125 molar hydrochloric acid? So our initial concentration, M1V1 equals M2V2. Our initial concentration is 12 molar. How much of that do we need is our V1. Our final concentration, we want it to be 0.125 molar, and we want 150 milliliters of it, so we want 0.150 liters. So to get V1 by itself, again, we're going to divide both sides by our 12 molar. And now we can see that our 12 molar cancels. So I'm going to take 0.125 times it by 0.150, and I'm going to divide it by 12, and I get a pretty small number. I get a volume equal to 0.00156, let's say. Let's change that back to milliliters because that's liters. 1.56 milliliters. And I put this in here because I want you to kind of understand here that we're starting with a really, really concentrated solution. This is the kind of stuff that definitely you don't want to breathe that. You definitely want to have gloves on. That's the stuff that if it gets on your skin, it's going to burn really, really bad. But notice that our final concentration is really, really low. A 0.125 molar solution of hydrochloric acid really isn't very concentrated at all. That stuff, if you get it on your skin, you probably won't even notice, that sort of stuff. Notice that to go from 12 all the way down to 0.125, you only need a milliliter and a half of it. I mean, you guys know by now how much a milliliter is. 1.56 milliliters isn't very much at all. So we're going to take our 1.56 milliliters and then we're going to add a ton of water, aren't we? We're going to take 150 milliliters of the whole solution. We're going to subtract the 1.56, and I think that leaves us with 148.44 milliliters of water. So we've got almost all water and just this little tiny bit of acid, of this concentrated acid that we added to it. And then we have created our solution. We've created 150 milliliters of 0.125 molar HCl.